Hello everyone. Today we're going to start our discussion of synchrotron radiation. Synchrotron radiation is a really important astrophysical process that's relevant in many different astrophysical conditions and plasmas, and it's kind of ubiquitous, so it's really important to understand. Now, each time we come up with a new radiation process that we're discussing, there are a few key things that we should keep in mind about that radiation process. The first and foremost is, what is the radiation process? So what describes the fundamentals of that radiation process? The second key thing is, what physical conditions or where in the universe might that process take place? And so this where has a couple of sub-questions, like where generally, like what kind of conditions might that process require, and where specifically, like what kind of astrophysical systems, specific systems, like say stars or galaxies, might that occur in. Then, once we have a sense of what those are, that's kind of the guts or the main aspects of the process, we'd want to know equations that describe the process. And equations usually tell us something about, for instance, the luminosity of the radiation process, like how much light can you get from the radiation process given the physical conditions. Now, always whenever using equations, it's all important to keep in mind what are the regimes of validity. And for that, we need to know what the assumptions are that went into deriving those equations. And as we go through, we'll keep those things in mind. We'll state those explicitly and just keep in mind those assumptions, because of course, in any given physical situation, if you are outside of those regimes of validity, then you cannot use those equations. And finally, I'll just write this as one word, how. This last question is how we can use this information about that physical process. What is it? Where is it found? Those equations and those assumptions, to then learn something about the universe. So say we receive some radiation, we know that it is synchrotron radiation. What does it tell us about the place in the universe that the radiation came from? Does it tell us something about the density? Does it tell us something about the magnetic field? And indeed, we'll find that those are two examples of things that we can actually learn about the universe using these equations under some assumptions. So for synchrotron radiation, we're going to follow a path that is similar for other kinds of radiation processes. If you've, for instance, seen discussions of thermal Bremsstrahlung, we follow a similar trajectory, where what we're going to do is we're going to talk about the dynamics. Then we're going to talk about the single particle spectra. And then we're going to talk about multi-particle spectra. Multi-particle spectra. And this will be clear what I mean by this in just a second. So before I dive into these details, I'd like us to take a moment to think about what this is for the specific case of synchrotron radiation. So what is it, where is it found, what are the equations, and it's fine if you don't know all of those right now, the assumptions and how might you use them. So feel free to take a moment to pause this video here and then just think about those specific aspects. Okay, so what is synchrotron radiation? Synchrotron radiation is produced whenever you have a charged particle, a fast-moving charged particle, in the presence of a magnetic field. So you have a magnetic field, and you have a charged particle, which is moving at some speed, gamma v, and there'll be Lorentz factors running around. And the moment you have a charged particle in a magnetic field, it spins around in the magnetic field, and we'll quantify this in a second, and it makes light. So that is what it is. So that tells us where it is found, of course, because it's found wherever you have magnetic fields and wherever you have charged particles. So indeed, you need both of these present. So for instance, at the surface of the Earth right now, in this room where I'm standing or where you're sitting, there is a magnetic field, right? The Earth has a magnetic field. But there are not necessarily charged particles running around because the air is mostly neutral on ground level. So you don't get synchrotron radiation. On the other hand, you could have a charged plasma, but maybe there are no magnetic fields. In that case, again, you won't get synchrotron radiation. It's only when both of these are present and these particles are moving fast that you get the synchrotron radiation. So that is what it is, where it is found. So what is specifically that this particle is going around, making loops in this magnetic field, it's making light. It's found wherever you have charged particles, magnetic fields. And that is many places in the universe. So the corona of the sun, galactic interstellar space, the space between galaxies, compact objects, neutron stars and black holes, relativistic jets. All of these places are places where you can get synchrotron radiation. Equations. So when we come to equations, and it's fine if you are not fully familiar with this yet, we'll break it down into these three aspects: the dynamics of the charged particle in the magnetic field, the radiation power and spectrum that you get from a single charged particle, and the radiation spectrum and power that you get from a distribution of charged particles. Because of course, it's never the case that you have a single particle. That's a nice toy model, but there's always a distribution of particles in any given region of space. Similarly, we talk about the assumptions when you do those derivations, and then once we have those equations, we can see how we can use them to learn about the universe. Now, as we go through this process, some of these will require aspects of theory or equations that you may have seen. If you're taking this as watching this lecture as part of a course, you will have come across those concepts before. If you're seeing this as not part of the course, you may need to go and have a look at those concepts before if you're not familiar with them. The other thing I'll remind you, again, depending on how you're coming to this video, is that I will typically, when I write down an equation, give you references, and those references we use for this video are High Energy Astrophysics by Malcolm Longair and Rybicki and Lightman. And these are the abbreviations I will use when I write down an equation. I'll give you the equation number so that you can go and find that equation later and check whether it makes sense to you. You can read the discussion above that equation, and that gives you possibly some additional information, additional context that you can use to learn more about this phenomenon. All right, so we're going to start through this process. We're going to start with the dynamics of synchrotron radiation. So when we're talking about dynamics, we are talking about what happens to this charged particle as it goes around this magnetic field. We'll see that it makes ellipses or a circular motion or spiral motion. We'll derive the radius of curvature of that spiral motion. We will calculate the acceleration on the charged particle, and that of course is very important because the acceleration is what enters into the formula that defines the power. We're going to Fourier transform that acceleration, and then that gives us the radiation spectrum. So let's talk about the dynamics of a charged particle in a single magnetic field. Okay, so we have a charged particle moving along some direction, gamma v, with respect to a magnetic field B. Now, in other radiative processes, you may have defined a direction with respect to the direction of the velocity of this particle. In the case of synchrotron radiation, there is already a direction given to us, and that is the direction of the magnetic field. So the moment you have a region of space and you have a magnetic field going through it, that magnetic field breaks the symmetry of that space, and so it makes sense to define your coordinate systems, your velocities, and everything with respect to the direction of the magnetic field. So I'm going to define my coordinate system. So let's put our z direction along the magnetic field, and then I'm going to rotate the plane so that the xz plane contains the velocity vector of the charged particle and the magnetic field. And that means that the y-axis in this case is out of the plane of the board. Okay, so feel free to take a moment to make sure that this makes sense to you, that this coordinate system makes sense to you. So in this case, the xz plane contains the magnetic field plane and the velocity vector. So two vectors, you can always define a plane. So now we're going to take this velocity vector and we're going to decompose it into the components parallel to the magnetic field, that's v parallel, and perpendicular to the magnetic field, which is v perpendicular. And so again, remember that this parallel and perpendicular is with respect to the magnetic field. And in other cases, for instance, if you looked at Thermal-Bremsstrahlung, those the conventions there are maybe with respect to some other directions. So just be careful here as to what parallel versus perpendicular means. So when we're talking about dynamics, the first thing we want to do is write down the equation of motion. So the equation of motion, of course, is tells us the change in the momentum, dp dt, which is just ddt of gamma mv, because this is a relativistic particle, so we need to use the relativistic free momentum, gamma mv. And gamma, this is the Lorentz factor of the particle, m is the mass of the particle, v is the free velocity. And this, on the right side, equates to the force. So think for a moment what that force might be. You have a charged particle in a magnetic field. So the relevant force in our case is the Lorentz force. So the Lorentz force in this particular case is, it's usually Q times E plus V cross P. So let's say this is charged particle I didn't define this as a charge of Q. So it's QE plus V cross B. There's no electric field, so it's just Q times V cross B. Right, so the velocity vector crossed with the magnetic field. So then what we can again do is break this velocity vector into the parallel and perpendicular components. And we can write this down. So that's Q V parallel plus V perpendicular cross with the magnetic field. And of course, the parallel component, when crossed with the magnetic field, goes away. And so you're left with the perpendicular component. And so this gives you Q V perpendicular B. And what is the direction? So to figure that out, you take the V perpendicular cross B. And you will see that it is in the minus y direction. So this is minus y hat. That's not necessarily going to be immediately relevant, but as we think about the dynamics, it's useful to just keep that in mind. So the magnitude is QV perpendicular B, and the direction is in the minus y direction. So because our velocity vector is the change in momentum is proportional to V cross B, that means that our force is at right angles to the velocity vector in the magnetic field. So that tells us that the force is perpendicular to velocity vector. And of course, this means that the force, this Lorentz force, does no work. And this is something that you're familiar with. The magnetic force does no work on the particle. So since the force does no work, that means that the magnitude of the velocity must remain constant. Right, so if the magnitude of the velocity remains constant, then gamma, which is the Lorentz factor, and just as a reminder, is 1 over square root 1 minus v squared over c squared, this Lorentz factor must also remain constant. Right, so that allows us, if looking at the left-hand side of this equation, to pull the gamma out of this derivative. And so we can write this as gamma m dv dt. Right, so we have gamma m dv dt is minus qv perpendicular times b. Okay, so now let's look at, so what we have on the right-hand side is the force. We can calculate the acceleration. So the acceleration, which is this dv dt, is taking the gamma m to the right side, minus q v perpendicular b over gamma m y hat. Right, so this is the acceleration vector in this particular case. So now, the direction of this acceleration vector, of course, is in the minus y direction. And you note that this acceleration vector is perpendicular to the velocity vector. Right? So this tells us, as we expect, that the acceleration is going to change the direction of the velocity vector, but it's not going to change the magnitude of the velocity vector. And you can see this by decomposing this acceleration vector into components parallel and perpendicular to the velocity, and you'll see that, of course, there's only a component that's perpendicular to the velocity. So what this means for our case is that the particle has an acceleration that's always pointed into the board that changes the, so that acceleration vector is perpendicular to v perpendicular, and it's perpendicular to v parallel. V parallel is not going to change as a function of time, but the direction of v perpendicular is going to change. And so what this will do is it'll make the particle do spiral motion along the magnetic field. And so you have the magnetic field this way, and then we have the velocity vector v parallel in that direction, and then v perpendicular, which is being the direction which is going to be changed as a function of time. So the acceleration of the centripetal acceleration that keeps this particle going around in a circle, that's, you can write it as a perpendicular, it's just the magnitude of this a, is, you can write that as v perpendicular squared over some r, where r is the radius of curvature, or is the radius of this circle, and that allows us to calculate this radius of the particle's orbit. Right, so let's write that down. So we have r, which is a perpendicular over v perpendicular squared, and of course we have our a perpendicular here, So that's Q. So it's the other way around, isn't it? It's V perpendicular squared over A perpendicular. And so that is V squared over, just looking at the magnitude, Q V perpendicular B over gamma M. And so that gives us gamma M V perpendicular over Q B. And so this R is known as, you may be familiar with, it has a name. This is called the Larmor radius. It is the radius of this circle that this particle makes. So just to keep in mind, this radius is not the radius of curvature of the path, because that depends upon the actual how stretched this spring is, how stretched this coil is. And that'll become important actually when we talk about the relativistic beaming effect that is going on in the radiation process a little bit later. But this is the circle this is the radius of the circle where if you were to turn this spiral edge on and then look at it, this is the circular radius that spiral would have. But of course, that can be stretched out if the V parallel is larger, then this pitch angle is smaller, and we'll talk about the pitch angle and the actual radius of curvature later. But this is the radius of that circle, as if this were being viewed edge on. Now, corresponding to this radius, there is a gyro frequency. So I'm just going to move that over here. So this gyro frequency is defined or called different things or has different symbols. I'm going to call that omega g for gyro. And this is the, how do you call it? The angular frequency of this particle in its orbit. So that frequency is just V over R, right? So V is R omega, so this is that omega. And so this, you put in that expression for R, and that gives us that this is QB over gamma M. So this is the angular gyro frequency of the particle in its orbit. All right, for some references, this equation here that I wrote down for the Larmor radius, this equation is 7.3 of high energy astrophysics. And then this equation that I wrote down here for the angular gyro frequency, this equation is equation 7.4 of high energy astrophysics. And then we can also write down I might be going off the board there. We can also write down a linear gyro frequency, which is just this omega over 2 pi, and that's QB over 2 pi gamma M. And this is equation 7.5 of high energy astrophysics. So this is relevant, this linear gyro frequency is relevant because this, as it will turn out, is related to the characteristic frequency of the radiation that we get out from this process. And so it's worthwhile keeping in mind what this looks like for specific cases. So of course we haven't defined what the charged particle is. It could be an electron, it could be a proton, and as we'll see later, the electrons are what are most relevant because they have the smallest masses and therefore they have the largest accelerations. And when you have large accelerations, you get a lot of radiation because the radiation power is proportional to the acceleration squared. And so electrons are really what do a lot of the heavy lifting in radiation in astrophysics. And so it's useful to put in the values for an electron, the charge of the electron, the mass of an electron for typical magnetic fields, and see what this looks like. So for an electron, this can be written as nu g is 2.8 megahertz divided by gamma for the magnetic field in units of Tesla. Sorry, that's magnetic field in units of Gauss. Sorry, it might be a little tiny. This is magnetic field in Gauss. Or it is 28 gigahertz divided by gamma for the magnetic field in units of Tesla. So if you know the magnetic field, like the Earth's magnetic field and some number of Gauss, you can put that in and figure out for a typical electron running around in that region of space, what is its characteristic radiation frequency? Of course, it depends on the speed of the Lorentz vector of the particle. Okay, so we are next, in the next little bit, we're going to talk about how all of this dynamics of this charged particle in this radiation space, so a charged particle in the magnetic field creates radiation, and how that radiation, what the spectrum of the radiation looks like, and what it looks like when you have more than one charged particle.